Evening, welcome to N Simplex Pachinko. I am Obi-Wan Pez, and tonight I'm looking to get into a little bit of something that I created. This was a few years ago. And I don't think that I covered this on our first night. At least I don't think so. No, we're doing calculus. Alright, so when you're looking at an absolute value problem, we're typically looking at something that looks like absolute value of x minus t is equal to, let's call it, I have a reason, but let's call it d. So really, what are we doing here? Well, what we've got is a particular target value, which I usually call t. And then you've got your particular landing value wherever you might end up being. We'll call it x. Doesn't actually matter where it is. It could be anywhere left or right of t. Typically it's not going to be right on it, especially if you're talking about like if we're doing like darts or something, because that totally looks like a dartboard. You can tell that I have not played darts in a long time because I don't even know what a dartboard looks like. So, in this particular scenario, this is two-dimensional, whereas over here we're doing a one-dimensional case, but basic principle still holds. You got the bullseye right in the middle, that's your target, and you have a dart that has landed somewhere, which when you throw the dart it sort of totally looks like an X, so we'll totally go with that. Alright, if you wanted to measure the distance that you are away from the target at the center, you would take some sort of ruler or something and line it up and try to measure out the distance that you are from one place to the other. So here we can do the same thing just on a one-dimensional line instead of a two-dimensional plane like this. And we say here we've got x is the value we landed at, and t is the value that we're trying to get to, our target. So that distance, whatever it is going to be labeled d. And what we really want to know is like mathematically speaking, how do we find out what d is? Or how do you find the value for d? So if you have actual numbers for x and t, you can then find the distance between them by subtracting their values. So if you wanted to know how far apart two numbers were, and this is any two numbers, so 2,843 and 5,796. If you wanted their distance apart, you could take any particular value. I know. Horrible that I'm reaching. And if we subtracted 2,843 from 5,796, we end up getting 2,953. Now, why would you probably... Let's try that again. So why would you probably subtract it in this particular order? Most of my students would probably tell you that, you subtract it in the order. You always take the biggest one and you subtract the smaller one from it just because. And yeah, sure, that's what we learned in elementary school. That's what you're supposed to do in order to figure out what the distance between these two numbers is going to be, or find their difference. All right, so find the difference between these two numbers, so subtract them. But here's the thing, if you went the other way instead, and you chose to do 2,843 minus 5,796, we would actually end up here with a negative value, but the subtraction is still the same. You're still subtracting the two numbers that we're talking about here. So this is still going to be a negative, in this case, 2,953. So you notice we get the exact same values from these two things. Which makes sense. If you start at one number and you go to the other, you've traveled this 2,953 distance. But the only thing that's different is the direction. So we've chosen to go in a different direction in the case where we subtract the larger number from the smaller one. But apart from that, everything's the same. All right, so where does that come in up here? Well, this means that we could take x minus t, but again, we are going to make a preference that x is going to be greater than t. Or we could take t minus x when x is less than t. All right, what about when they're equal? Okay, so if they're equal, then you end up getting a 0 no matter which one you use. So it's kind of arbitrary which one you choose to put the equality sign on, but I generally speaking will put it on the one that is where x is greater than t, or x minus t as a term is going to be greater than 0. So this is actually the definition of a piecewise function. So there are two separate pieces to this, one where x is greater than or equal to t, and one where x is less than t. That's the other way for you. Sorry, x is less than t. No, that's the right. Oh, man. X is less than t this way, or x is greater than or equal to t this way. Okay, and this is the definition of the absolute value of x minus t. Now I like to change it just a little bit so it looks a little bit nicer, and this will align more with what you all probably have done in your math classes in high school or what have you, probably even colleges. Here, instead of having t minus x, I'm going to switch this around and make it a negative parentheses x minus t. And then these, I'm going to bring the t over to the other side, so it's x minus t is greater than or equal to 0, or x minus t is less than 0. So what did this do? Well, realistically, it didn't change anything. However, it changed the intent. It changed the focus of what we're trying to look at. What this is telling us is that for absolute values in general, for anybody who doesn't quite understand absolute value or whose knowledge of absolute values is limited to it makes things positive, this is why it makes things positive. Really, it makes things non-negative, but so the absolute value of x minus t is going to be equal to the piecewise function x minus t, just the normal subtraction, if that value, x minus t, is a positive or 0 value. so non-negative. Or you have to switch the sign on this number x minus t if x minus t is less than 0 or if x minus t is negative. So the interior of these parentheses is negative, which then comes out and hits another negative and switches it to positive. So that's exactly what we want for this. If you have a negative value inside the absolute value, it switches its sign and becomes positive. So that's what all of this really means. So I'm all for like much deeper learning on any mathematical topic, but especially like absolute values like this. Oftentimes students are just told to do something as a skill or as a process, and it's not really well understood. Okay, so where does that take us? So we've got this absolute value, which is telling us to, again, just do the regular subtraction if the stuff inside is positive, or to switch it to a positive if it is negative. Now, in this case, what we can do is say algebraically, we had this original x minus t is equal to, absolute value of x minus t is equal to d, the distance that we're traveling. Well, now we can replace the left-hand side, our absolute value of x minus t, with this stuff. So we're going to have just x minus t is equal to d when x minus t is greater than or equal to 0, or negative parentheses x minus t is equal to d when x minus t is less than 0. So I tell my students this is really where you want to be when you start looking at absolute values and trying to solve this algebraically. You want to take all of these terms, and instead of, because I know what you were taught, I was too, you were probably taught you do x minus t equals d, or x minus t equals negative d. Now, this doesn't work in the way that I've said this for a couple of reasons. One, your distance, generally speaking, is not going to be negative. You could make it negative and just say, well, this is kind of d in the negative direction, or you could let it be, that doesn't look like a d to you, does it? Okay, I need to stop going so high on the screen. Okay, so you could say that this is d on this side, and so negative d is just going to be in the opposite direction, so it would be a negative d up this way. That's okay, I guess. Or you could say, again, here, we just want what the absolute value of the distance is. So instead of saying that the stuff on the inside is a positive d and the stuff on the inside is a negative d, we could rearrange this as I did here and go more with the definitional, well, more by the definition of what absolute value really means. So take the stuff on the inside, just do the subtraction if it's positive, and switch its sign if it's negative. Anyway, I prefer this, obviously. That's why I'm doing this whole thing. All right, so if we do this, this means that here we're going to add, let's do green, going to add t to both sides. And this means that you get an x plus 0 is equal to here d plus t. Or down here, I will distribute the negative onto this side and make it a negative x plus t equals d. And I'm going to rearrange this probably in a way that you're not going to be used to, but it makes sense later. I'm going to add x to both sides, and I'm also going to subtract d from both sides. Reason being, if I do that, I now have t minus d is equal to x. And up here, probably want that the other way around. So you'll see why in a minute. This is going to be t plus d. So what does that mean when we bring these together? That means that x is going to be equal to t plus d, or x is equal to t minus d, which if you want to write it in shorthand, this is x is going to be equal to t plus or minus d. And on a graph, this then makes it t, our target values in the middle, our x values, the places that we want to have, are going to be a d in the positive direction, or a d in the negative direction. So going up, that is going to be t plus d. Going down, that is going to be t minus d. And we want specifically these individual locations. All right, so this doesn't give you any actual like numerical solutions or anything like that. This is just all completely algebra. So doing everything 100% abstract, you will get these two things as your answer. So if we want to do that as concrete answer, a concrete problem, you could do something like, let's put that there so I don't forget. The absolute value of x minus 4 is equal to just 1. Let's do something easy for now. So absolute value x minus 4 is equal to 1. We're going to say here that this is, again, just like we did algebraically over here, x minus 4 is equal to 1, or a parentheses negative parentheses x minus 4 is equal to 1. Here, again, add 4 to both sides. We get that x is equal to 5. Or distribute the negative. We get a negative x plus 4 equals 1. Subtract 1, add x. All right, here we get a 4 minus a 1 is 3, is equal to, and over here 1 minus 1 is 0, plus x is x. So we get x equals 5, or x equals 3. And in set notation, that is x equals either 3 or 5 in curly brackets. Okay, well, this isn't what I invented. This is just the standard kind of way to solve things algebraically. So why am I getting all excited about inventing something? Well, I decided here that I would end up realizing, or I could realize, based on all of this other work that we did up top, talking about the distances and absolute values and what it really means and target values, that we could just jump basically from the beginning of this problem all the way to this number line solution here. So we know, okay, I'm just going to do this right now just as x. We have a target value, which in this case was 4. We have a distance up of 1 and a distance down of 1 to both 3 and 5. and we are at those two locations, 3 and 5. So we can draw points at each of those, and there we go. This is, again, the number line solution. Again, not like it's terribly difficult or anything like that. It's just like, obviously that's what we got, right? But you can get there from anywhere. So let's say that we have 2x minus 5 is going to be equal to 7/3. All right, this is gross, but this whole thing will still work. What we're going to be doing is trying to find the distance between, because we're subtracting, we want the distance between these two things, 2x and 5. So we don't know where 2x is on the number line, so we're going to try to find out where 2x is. So put it on the end there. It's part of that. And 5 on the number line, we know exactly where that is. Just put it in the middle, because you want to get points that are around it. So the distance between 2x and 5 is equal to 7/3, which means that the distance that we have to travel is 7/3 in the positive direction and also in the negative direction. We don't know which way we need to go, so we're going to choose to look at these as one going up and one coming down. All right, so then what we're going to do is say, what is 5 plus 7/3? Well, 5 is 15/3. So plus 7/3 this way is going to be 15 plus 7 is 22. So 22/3 going up. And this is equal to, so we want the points that are exactly that distance away. So 22/3 is one of our solutions for this. Then when we go downward, we're taking 15/3 and subtracting 7/3. This is going to get us then 15 minus 7 is 8. Our units are thirds. So 8/3 coming down, and again, that is a solution for this particular problem. However, this is not actually finding x. We wanted to find x, but we have found the solutions for 2x. So in order to find the solutions for just x, we need to divide by 2. And in fact, we need to divide all of this stuff by 2. All distances, all values, everything is being divided by 2. So then, this is going to get us a new number line if we want to clean this up a bit. This is x. Our target value is 5 divided by 2. 5 halves, 2.5. We go up, and this is going to be 22/3 divided by 2 is 11/3, or otherwise 22/6, which then simplifies. So 11/3 going up. Coming down, we have 8/3 divided by 2 is going to be 4/3, or again 8/6. It's going to simplify. We had solid points at each of those values. And we also had a distance between these of now 7/3 divided by 2 is 7/6. So number line wise, this kind of pseudo graphical method is showing us that we get these two values, x equals 4/3 or 11/3, as our two solutions. I haven't done any like seriously hard math here or arithmetic or anything like that. This is just a calculation of taking this target value that was in the middle. We add and subtract the distance, as it says in the actual problem. And then when you add or subtract the distance, those particular values are taken because of this symbol between. So the distance, the absolute value, is equal to, has to be exactly 7/3. And those are the acceptable solutions. So it's like the dartboard up here. If you said that this distance exactly was 7/3, then all distances surrounding the bullseye at 7/3 are going to be an exact circle around the bullseye at that distance, at that exact same distance as that dart. So the same thing happens on the number line. You have a target value, and now you draw a circle with a radius that is exactly 7/3. And how many times does it hit that number line? Well, once out here, and once out here. So, two possible solutions. Let's just mark that there. Okay, now if you want to see it algebraically, again, absolute value 2x minus 5 equals 7/3. This is going to now take a backseat to my method because, quite frankly, I like it better. So, this means that 2x minus 5 is going to be equal to 7/3, or a negative parentheses, 2x minus 5 is equal to 7/3. This is going to add 5 to both sides. 2x is equal to 7/3 plus 5. Well, we already did that. This is 15/3 plus 7 is 22/3. Or this is now going to be a negative 2x plus 5 equals 7/3. Add 2x and subtract 7/3. Okay, now we get a 2x on the right is equal to 5 minus 7/3. Again, in this case, this is 15/3 minus 7/3 is 8/3. And divide all of this stuff by 2. X is equal to 11/3, or x is equal to 4/3. Okay. Now we get these two solutions, and you might say, okay, but it's not like super impressive. It may just be, the order in which you put these on the page. So it's a fair concern. So at this point, we want to also make sure that we are able to do this with practically anything that we want to put into an absolute value. I will say that the easiest type of problems and the ones that we typically look at in my pre-calculus classes are that we are just having linear functions on the inside of these absolute values. All right, so what if we trade stuff around? What if we put fractions in? What if we do all sorts of stuff? Doesn't much matter. So absolute value of 3 minus 2x. Let's do a more interesting one, 4x. Is, let's do less than 1. Okay. Well, this has changed in two ways. One, we've swapped the variable and the constant, and we also now have an inequality rather than an equality, an equation. So what we're going to do here is just look at this and say, well, we want to find the difference between, so we're subtracting, find the difference between 3 and 4x. That didn't change anything, really. Big picture-wise, it's all the same. So here we've got the difference, or the distance between 4x and our target value of 3 must be less than 1. So if our distance is 1 away from 3, this means that going up is going to be 4, going down is going to be 2. Then, in addition, we want the distance here to be less than 1. So from this point, we want all of our valid solutions to be within this distance here. So that means that all of this stuff between 2 and 4 are going to be our valid solutions. And what about 2 and 4 themselves? Well, they can't be equal to 1. It's just strictly less than 1. So we need everything to be within this interval and not including 2 and not including 4. Okay, and then like before, we need to put this back to just x. So divide everything by 4, including our distances up here. And then we just have to rewrite and simplify. So we have a 3/4 in the middle. On the upper end, we have a 4/4, or 1. It has an open circle, and it's shaded back to the inside. If we go back the other way, 2/4 is 1/2, open circle, and shade inside again. This distance here is 1/4. This distance here is also 1/4. Now again, it doesn't particularly matter. You could have left this as, or you could have not even put distances or the target value in the center. You don't need them as far as like trying to find out what the answer is. Our solution here is an interval, which can be thought of as finding the values which are acceptable, which start at 1/2 and lead up to 1. They're both open. The epsilon symbol that I'm using here just means that x is going to be a member of the set that is given by the interval, open bracket, 1/2 to 1, open bracket. So this is accepting any values between 1/2 and 1, not including their endpoints. All right, if you don't believe me, that's perfectly fine. We can do this algebraically too. So 3 minus 4x is going to be less than 1. Now the thing that most of you probably learned is you go to the other side and you say, okay, 3 minus 4x is going to be greater than -1. And to that I usually say why. Ask my students why. I ask them all why a lot. So when I ask why, a lot of them are stuck here because they just can only answer with, well, because my teacher told me, and that's what I'm supposed to do. Okay, fair enough, that's what you learned. But if you follow the rules that I showed you earlier, you actually keep this exactly the same. You're just replacing the absolute value with 3x minus 4 and its negative version, negative 3x minus 4. Nope, 3 minus 4x, sorry. 3 minus 4x, and also negative 3 minus 4x. And that's all you do. You didn't change any of the problem. You kept it exactly the same. And I highly recommend that you do this as well. So any of you students out there who are still doing, pre-calc stuff, or maybe upper level students who are looking to up their game in understanding what this mathematics is all about, your absolute values, just use the definition. Use the piecewise definition. So absolute value 3 minus 4x can be 3 minus 4x or negative 3 minus 4x. Now you'll notice that I did in fact leave out the word that goes in between them. This is something that I don't do lightly. All right, you'll notice that in the other ones I've always put it in there. The reason that I skipped this is because you may not know exactly what you're supposed to do here, because OR is not the only game in town. You've also got the possibility that it could be AND. Okay, so an AND is a possibility, and now you have to figure out which one you're going to use and why. So the way that I would probably do it is look at what kinds of solutions you get. You could also actually solve this. All right, so I am making my x's positive. This is going to show us that we get a 3 minus 1 is 2 is less than 4x divided by 4 divided by 4. So this is a 1/2 is less than x. Notice that I also didn't have to change the sign that's here. I just kept it exactly as it is. The only thing I'm doing is I'm moving the variables around to make them positive. Always. Every single time. Over here, same kind of deal. Negative 3 plus 4x is less than 1. X's are already positive, so move the 3. This is going to be a 4x is less than 4. Divide by 4. X is less than 1. Now, at this point, this is where you'd say, okay, seriously, what are we putting in between here? If you know your number line and how to draw it properly, you've got a 1/2, you've got a 1. You know that x has to be greater than 1/2, or 1/2 must be less than all valid x's. So if 1/2 is less than all valid x's must be to the right of it or greater than. So this one by itself would get us all numbers greater than 1/2. This one by itself would get us all numbers less than 1. Now, if you do or, all we care about is all solutions that are going to be in one inequality or in the other. If we take or at this point, this is going to include everything to the left of 1, and this will include everything to the right of 1/2. That doesn't cause us to miss anything. This, if it were an or statement, would cause us to cover the entire number line. Now, if you look at what we were talking about before, this says that we wanted only the values that were within a distance of 1 from 3. So clearly this is not working, or, well, after it gets translated, it was within a distance of 1/4 from 3/4. So this is not working for us because this is including all sorts of stuff that's way outside that range. So that doesn't work. So then you go back. Undo, such a wonderful thing. And you say, what about and? Well, an and statement includes only those things that satisfy both pieces of this argument. So we have stuff that is to the left of 1 and also to the right of 1/2. Where does that leave us? Well, it can't be at 1/2 and it can't be at 1, but it can be everything to the right of 1/2 and also to the left of 1. So that's everything in here, which means that this is an and statement, and we can translate that back up here. Now, how do you tell ahead of time? It's actually pretty easy. If you think of absolute value in terms of distance, then you want all values where the distance is going to be less than a certain value. So if distance is less than a certain value, then our target value in the middle is going to end up having all of its acceptable solutions close to it. So it has to be within these values. In this particular case, this one is, again, the open bracket at 1/2 to 1 open bracket again. So all acceptable values are within this interval. If, on the other hand, if we had something that was greater than, we'll see that next, then we want our distance to be greater than that. So the distance from the target value, we need to be outside of that distance. So all this stuff that away. That away. So we get stuff that is off to the left. That's your right. Off to the right and off to the left of those values. So when I talk about this, I usually talk about border points, which are going to be those that are on the edge of the intervals in question. So we have border points at 1/2 and 1, and those border points in this case will be hollow, and also all acceptable values must be within those borders. Okay, so now what about, let's try something else, right? What about absolute value of 1 plus 3x is greater than or equal to 7. Doesn't really matter what you pick, right? All of this should work regardless of values. So with this, I'm going to say here, we still want to subtract. So we could change this to subtraction, but this is going to make our x term negative. And quite frankly, I don't like my x terms to be negative. I think you probably have noticed that so far. So instead of making this x term negative, I'm going to translate this and say, you know what, let's do the commutative property of addition and just say that this is the absolute value of 3x plus 1 is greater than or equal to 7. Which means that the absolute value of 3x minus negative 1 is greater than or equal to 7. Okay, now it's just like all of these other ones that we did. So over here we're going to say we've got a number line. It has a variable term of 3x. We're trying to find the distance between 3x, which we don't know where it is, and the value negative 1, which is here. That's our target. The distance that we want must be greater than or equal to 7. So find the borders. It goes 7 to the right. It goes 7 to the left. Find the borders. 7 to the right of negative 1 is going to be 6, or add 7 to it. 7 to the left of negative 1 is going to be negative 8. Again, subtract 7 in that case. And the distance that we want is greater than or equal to. So we can be at these border points because it says it can be equal to that distance. And also the distance must be greater than that. Hey, Lana. So if the distance is greater than 7, it's going to be to the outside. Willkommen aus Chat. Yeah, whiteboard was having some trouble at the beginning, but we got it squared away. Okay, so now this is saying that our solutions for 3x must be outside of negative 8 and positive 6, which then again, just like we said before, if we divide all terms by 3, we're going to get x, again, for our variable term. Middle is going to be at negative 1/3. The right is going to be 6 over 3, or 2. It's going to have a solid circle with a line going to the right. And negative 8/3 on the left, can't simplify. It's going to have another solid circle and shade to the left. Yeah, my initial stream announcement also said that I was playing games tonight. That was a lie. Apologies to anyone who is thoroughly disappointed. And then our distance here, again, you don't actually need to write it, but the distance here is going to be 7/3. I find it useful to at least figure all this stuff out so it looks a little bit better. It also looks like you know what you're doing. And the x values here are going to be from negative infinity, which is going to have an open bracket. No. No. No, my regular actual office hours are non-public, because that would be a massive FERPA violation. All right. So open bracket negative infinity up to negative 8/3, and have a solid bracket here which says that we can use this particular value, negative 8/3, union with which union is just the same as putting a big or in there. Bracket at 2 all the way up to positive infinity. Open bracket. Anytime that you have a solid number that you are stopping at and it is definitely being used by the problem in question, you can use that square bracket. Anytime that you have a number that is not actually being used, you can't technically plug it in and get a solution back. So infinity or negative infinity, you don't actually get a solution. Or if, like on this previous one, 1, if we plug in 1 over here, we get 3 minus 4 times 1 is going to be 3 minus 4. So negative 1, absolute value is 1. 1 is less than 1 is a false statement. And again, infinity, you just can't plug it in. It doesn't really work. You could do some stuff with limits, but we're not going there today. All right, so that's what we get for this type of thing. Again, this is my crazy invention here. This whole idea of taking this other stuff that we had up top and rearranging it until it looks like you're saying, let's find the difference between these two numbers. One of them is a positive variable term, and the other one is just a numerical term. Once you do that, then we can say, all right, find the target, find your distance going out from that target, and then find what the values are going to be. Again, in this case, greater than or equal to that particular distance. So it's going to be outside of that particular range, outside of those border points. All right, there's one other kind of type that sort of works usually. And that's when we do something crazy like 5 minus 3x is less than 2x plus 1. So this works a lot less well with my number line type stuff, but it still works. So it's usually okay. I forgot to do that one algebraically, but whatever. Most of you probably understand by now how to get it, so it'll work. All right, so when you do the number line here, we again look at this and say we are trying to find the difference between 5 and 3x, or the distance between 5 and 3x. The distance going up is going to be 2x plus 1, and going down is also going to be 2x plus 1. Now this becomes a little bit trickier because technically I don't know which way is which. If 2x plus 1 is a negative value, then we might technically be in trouble. If 2x plus 1 is a positive value, then it's going to behave just the same as what we did before. So, what we're going to do then is, let's just think about this real quick. So 3x minus 5 is going to be shifted to the right. Yes, so it will intersect. This is good. Yep, I think tonight we've also got time to do a slightly different one. So, okay, so in theory, again, this is going to be, well, it's definitely going to be here open and here open. The thing we don't technically know at this point is whether this is going to actually mean that it is within this area or outside. Just from the number stuff that we did, it should be within. So, should be. But again, based on the variable value, it could, in theory, be not that. So we want to be careful at this point what exactly is going on. This is going to be 2x plus 1 plus 5, or 5 plus that. And this is going to be 5 minus parentheses 2x plus 1. I should have done it that way. Five plus parentheses 2x plus 1. All right, so this is assuming 2x plus 1 is greater than or equal to 0. If it's less than 0, we got a problem because, again, distances, generally speaking, can't be less than 0. So, yeah, we'll get no solution there. However, again, just thinking about it, I did find that this is going to have an intersection point with this. I will show you how I did that in a full graph and probably in my other method of graphing. There's time, but at the same time, it's kind of like I want to save it for its own thing. All right, so this is going to be a 2x plus 6. This is going to be this is 5 minus 1 is going to be 4, and that's going to be a negative 2x plus 4. And again, this is sort of where my method kind of breaks down a little bit, because it's not going to be so easy as just getting numbers. Instead, what we've got now is we can't be here, but again, we think it's on the inside of all this stuff. So this says that, in theory, 3x should be less than 2x plus 6, and 3x should be greater than a negative 2x plus 4. Again, we think. We'll make sure that when we do this out, actually algebraically. So actually do this one algebraically. All right, let's remove that. Absolutely. All right. So if we subtract 2x from both sides, we get x is less than 6. And if we add 2x to both sides, we get a 5x is greater than 4. All right, divide by 5, both sides. X is going to be greater than 4/5, and x is less than 6. So that says that we're going to have this 5, we're going to have the 3x there. Nope, we already found the solutions for that, so that's just going to be x. And this is no longer going to be 5. And again, we don't actually need that now. So we had 6 at the top end and 4/5 at the bottom. We had open circles at both and shaded in between. So this one's a little less interesting. It still gets you a little bit of something that you can work with, but again, it's okay. So x is going to belong to the set from 4/5 up to 6, not inclusive. Okay, so let's actually go through this algebraically then and make sure that that's actually the answer we're supposed to get. So up here we end up with a 5 minus 3x is less than 2x plus 1, and again in theory 5 minus 3x, keep that side the same, is going to be, make that a negative, parentheses, 5 minus 3x is going to be less than the same 2x plus 1. Sure, that works. Right. It's all good. I wrote too big anyway. All right, so we want to make our variables positive. So add 3x to both sides. That means get rid of this 1 from here, subtract it from over there. We get 4 is less than, this is going to be 5x. Oh, good. So we're getting the same thing. That's a plus. So 4/5 is less than x. And again over here, this is going to distribute, make a negative 5 plus 3x is less than 2x plus 1. We can subtract the 2x from here and add the 5 from here. So subtract 2x, add 5. This is going to be 1x less than 6. So yeah, we ended up getting the same things on both of those. All right. Well, good times. All right, so if we want to check it just real quick graphically, 5 minus 3x as an absolute value. You could do this real quickly on paper. You know that this is negative 3x plus 5. So it has a slope of negative 3, which is pretty steep. And then as soon as it becomes a 0 value, this actually causes it to reflect off of the x-axis. So we get something like this, which goes up like that, and up like that. This value here is the 0 of the line y equals negative 3x plus 5, or 5 minus 3x, however you want to say it, which is x equals a 5/3. So if you plug in 5/3, the thirds multiply by 3 to get 1, and then you're left with a 5, which 5 minus 5 ends up being 0. Okay, so then 0, 5, we got a point, and also at 10/3, we're also going to be back up to 5 on this side. Not that you need to know that necessarily, but can be helpful. And then we want to know when it intersects the line 2x plus 1. So if we split this into fifths, 3, 2, 1, not too bad. A slope of 2 is a bit shallower compared to that, but not that much. So we get a value that's up here, roughly speaking. All right, by the time we go 5/3 over, we're going to go 10/3 up from here. So that's 1, 2, 3, and a little. So we're going to be here. By the time we go another 5/3 over, it's going to be another 10/3 up. So 1, 2, 3, and a third is going to be like there compared to here. So yeah, get this. I could use the ruler, but at the same time, this is a sketch, not an actual graph. All right, that's going to go that way. This is still steeper, and eventually these two things, nope. Eventually these two things will intersect at this point here. So we found that our x value for this is at 6, and our first x value was at 4/5. This being 5/3, that's 1 2/3 or 1.6. This is 0.8, so it's like halfway, give or take, and that makes sense. Ish, you know. Not perfect, but. So at the very least, this makes at least some intuitive sense. This is kind of what I was doing in my head. And like I said, I want to talk about function transformations sometime in the future, just because they're awesome. And people could probably use some extra hints on how to do it, or definitely how to use it. All right. So Lana, anything in particular about logs? Just like what it means, start from the beginning. Alright, so to start our journey toward logarithms, first you got to know a few things about other stuff that's going on. So here we have an exponential function. An exponential function, for anybody out there who doesn't know, just is basically saying that we're going to take b and we're going to multiply it by itself x times. So we got some list of b's that are constants that are multiplying themselves together a variable number of times, which is why x is in the exponent here. All right, so that creates an interesting scenario, in which case you've got, like, 2 times 2 times 2 times, etc. If we're doing this x times, then that's going to be 2 raised to the x. If we're doing like 3 to the x, that's going to be 3 times 3 times 3, etc. Again, x times. I guess technically I want the last one. It's a finite number, so you do actually need the last number. All right, and if we're looking at exponentials, we can say, we have y equals b to the x. This can be transformed by multiplying and adding and subtracting and doing all sorts of various things to this function. Or the other thing that we can do with this is we can find its inverse. So a lot of you probably remember the old switch the variables and then solve for the other one technique. I don't like that very much. Not at all. So instead, what I would like my students to do is say, all right, I've got y and x in these particular places, and I need to reverse them because an inverse of a function so we'll call it a functional inverse. The inverse of a function is what happens when your variables, your x and your y, or inputs and outputs, whatever you're going to call them, end up getting switched. So instead of y being your output, y is then going to be your input. Again, functional inverse says that a regular function, f takes a set of inputs and maps them over to a set of outputs. And that mapping is called f. If, on the other hand, you want to reverse that process and take your outputs and reverse them back to inputs, this is going to be the functional inverse, f inverse. It's not actually raised to the negative first power, it's just that's the notation somebody chose. Probably Leonhard Euler, if I'm honest. So the mapping, that mapping is essentially backwards of what the initial mapping was. All right, so what we want to do then is reverse where our x's and y's are. I will say that let's do it this way. So f of x is equal to b to the x. Let's take the functional inverse of both sides. When you take the functional inverse of a function itself, it becomes x. And the functional inverse of an exponential has to include the base that we're talking about, because this could be on a base of 2, it could be on a base of 3, it could be on a base of 500, it could be on a base of like 0.5. So there's practically any number of things that you could do here. And then you're going to have to say, okay, well, this is the functional inverse with base b, because this is the function with base b. I'm just going to put that as a subscript. So then here, what this is saying is that it's going to undo an exponential with base b. So unfortunately, I just put myself directly into a corner, because this is undoing the exponential with base b, which leaves me with an x. So x equals x. Okay. Hooray! Let me back up a little bit. So instead of doing the f of x here, let's actually keep that as y. All right, there we go. So we undo the exponential with base b, has an x as its exponent, and whenever you take a function and then take its inverse, they undo each other and you get x back. Then over on this side, this is the interesting part. You have the functional inverse with base b of y now. We've already solved for x, so this is our inverse function, which we haven't technically named or anything like that. But we know what it's called, right? That's the reason we got here. So this is a logarithm with base b of y equals x. Many of my students hate this next part. X is now a function of y, so we'll call it g. Or we could actually just call it the all right, or we could leave it as the functional inverse of y, because it's already that. Oh man, it was that up here. This is fine. All right, functional inverse base b of y. So if we write this now in that shorthand, functional inverse base b of y is equal to the log base b of y. I don't know about you, but I don't really like having a y as my independent variable. So in order to compare the original function and this function, I'm going to just change the variables, because it doesn't matter what variable is on the inside of the function, provided that you match it everywhere that that variable existed in that function. All right, so that this would have been y equals the function of x, f of x, which is then equal to b to the x. Okay, so if we had actually involved that notation from the beginning, that would have been helpful. So anyway, f of x equals b to the x. F inverse base b of x is going to be log base b of x. Now, I suspect you weren't really asking about the derivation of logs, but you know, sometimes it's a little worthwhile, especially for anybody else who's hanging around and doesn't quite understand what logarithms are. But it's all good. So basically, what logarithms are doing, if you notice back here, we had this x that popped out as now our dependent variable. That was the exponent on the original base. So if I read this going across, let's take this part. Okay, so this was x equals log base b of y. This would have been what exponent on a base of b gets me y. All right, so x is the exponent in question. If we do this just with actual numbers, right, the log base 3 of 9, for instance, keep in mind this is not an exponent on this little 3 here. That's not how it works. This is, again, asking a question, what exponent on a base of 3 is going to get me 9? Well, this one's a nice easy one. We know that 3 raised to the second power is 9, so the exponent 2 on a base of 3 gets me 9. If we want to rearrange, it is equivalent to rearranging this thing to 3 raised to the second power equals 9. So these are completely interchangeable with each other. So if you want to go and like just randomly do any sort of problem, you know, with random variables and numbers and stuff like that, you could do like log base 2 of 3x. Yeah, whatever. Okay. Equals 7. And if you wanted to rearrange this in order to solve for x, this is actually possible. You could say, okay, well, this is going to now be 2 is my base. The exponent on a base of 2 was the thing outside over here, so that's 7. So 2 to the 7th is going to be equal to 3x. 3x is what is the exponential term. Your 7 is your exponent on to your base. I guess I don't need that one. I can actually draw this over. So the exponent of 7 on a base of 2 gets me the thing that's on the inside of the parentheses for the logs, so 3x. And then again, in this case, you can actually solve this problem. Here you divide by 3 on both. You get 2 to the 7th is 128. So 128 divided by 3 is 42 and 2/3. That took me too long. And I hate mixed numbers, but in this particular case, I'm just doing quick and dirty, so yeah, it works. All right, so then there's all sorts of things that you can do with this. I usually use this to prove all of the exponent rules and log rules that work with all the exponential and log rules, which include stuff like, okay, what happens if we are to just framing, I don't want to go outside of that. So what happens if we are to, let's say, take that one that we had before. So log, let's do log base 2 of, sure, why not? Let's do that 3x that we had in the previous one. So one of the things that we can do here is say, all right, we don't know what the exponent is on 2. However, what we sort of want this to be is that our 2 is showing us what form our 3x is going to be in. So if you want, you can come up with a dummy variable like a. And this says that 2 to the a power is going to be equal to 3x. Now, I'm not doing this intentionally to solve for x. I'm actually doing this intentionally to solve for something else. So, in order for 3x to be of the form 2 to the a, what I'm going to have to do is convert 3 and x, or 3x as a whole, to something that looks like this. That looks like 2 to a power. So that's somewhat inconvenient for these particular numbers. You could just do this generally with, like, x and y, or 3 and 5, or whatever you feel like. It doesn't really matter. I'm just doing 1 as a number and 1 as a yeah, 1 is a number and 1 is a variable. Just kind of works. I don't know. All right. So what I want to do is say let 3 be equal to 2 to the m, and let x be equal to 2 to the n. Okay, so if I do that, might be a little bit of a stretch, it's fine. If we do that, then we say that this is going to be 3 is equal to 2 to the m times x is now equal to 2 to the n. When you multiply two like bases together, you add their exponents. So this is now 2 to the m plus n equals 2 to the a. Well, this means that a is equal to m plus n, because if our bases are the same, then our exponents must also be the same. This comes about because they are one-to-one functions, and I should probably mark that. All right, so you're only able to take these out because they're one-to-one, which means that if we had, for instance, f at, let's use letters I'm not using, f at p is equal to f at q, then this will imply, and in fact both ways, that p is equal to q. I guess the upward direction is rather trivial, but downward direction is much more important for what we're doing here. So the inputs to these particular functions, the outputs to these particular functions, in this case the exponentials, are going to be equal. That's given. So therefore the inputs need to also be equal. They're a and m plus n. All right, now we can backfill m and n. Now we don't have a thing as far as what they're actually going to be equal to, but we can translate them back to logarithmic form. So here m is equal to the log base 2 of 3, and n is equal to log base 2 of x. A was equal to the log base 2 of 3x. M was equal to the log base 2 of 3, plus n was equal to the log base 2 of x. So this proves a fundamental rule for logarithms, in that if you have a term that has multiplication on the inside of the log, you're then able to break this thing down Because, again, what we were talking about before, these are exponential terms. These are things that are of the form whatever this whatever the base is raised to whatever the exponent is on the other side. You're then able to split those up with logarithms. And you can say that if you're multiplying there we go. If you're multiplying two terms that have like bases, your 2 to the m and 2 to the n, you're allowed to add their exponents together. Well, logarithms are exponents. So you're able to add their logarithms together if you're multiplying their like bases together. The 3 and the x are technically like bases on base 2. As long as as long as you're doing the right math here. As long as you keep the same base on your logarithms all the way through, you're able to split the logs individually into their separate multiplicative terms and add them up, because you are, again, logarithms are exponents. Multiplying your like bases means that you can add your exponents. So split the logs. And this also works in reverse in the exact same way. If you have two logs that are being added together, you're then able to say, okay, well, they're being added, so now I can bring them back together as if they were like bases and multiply those like bases together. So this all ends up being the same here. But the underlying rule is that if you have any log base b of x times y or anything remotely similar, you're able to split the logs over addition. So this is fundamental rule number 1 of like playing with logarithms. Same sort of stuff happens if you're doing, I mean, there's all sorts of things, but if you're doing something like log base 2 of x to the third, so the 3 is now an exponent instead. Well, this is an exponential term. Again, we don't know what it is, so we'll just call it a. Once we do that, we can say that, okay, well, if we rearrange this, this is 2 to the a is equal to x to the third, and we're going to let x be of the form, again, 2 to the m. If we do that, then this is 2 to the a is equal to 2 to the m parentheses to the third, and now you're able to multiply your exponents together. When you raise a power to a power, you multiply their exponents. So this is 2 to the 3m equals 2 to the a. And again, take the logs of both sides, or you say here that these are one-to-one functions, so if their bases are equal, their exponents must also be equal. So a is equal to 3m, where a is equal to log base 2 of x to the third, and m is equal to log base 2 of x. So this is 3 times log base 2 of x. So this is fundamental rule number 2. Anytime that you have exponents on the inside of a log, that's the same as having a power raised to another power. So then you're able to say, okay, well, I'm going to take that secondary power, the one that's on the inside of the log, and I'm going to multiply it on the outside instead, because we are multiplying our exponents. Logs are exponents. So the 3 on the inside for an exponent becomes a 3 on the outside for a multiplicative term. So this is here. And again, fundamental rule number 2, log base b of x to the n is going to be equal to n log base b of x. Ooh. Maybe it worked. Okay, nope, apparently. Oh, I hit the... It was worried I was touching the button. Okay, so this is fundamental rule number 2. Now, fundamental rule number 3, they usually give you back here. They do, okay, let's do multiplication and let's do division right after. But they don't actually tell you why it works. So again, I'm big on why. I'm going to go the exact same way as we did here. Actually, that's a lie. I'm going to use what we found here in order to do division. So if we do log base 2 of 3 over x, so this is a rational function. What I'm going to do is say, you know what, I'm not even doing the a thing and trading stuff for logarithmic or exponential terms. I'm just going to do log base 2 of this 3 over x is the same as 3 times 1 over x, which is the same as log base 2 of 3 times x to the negative 1. This is an exponent. I know how to do exponents. All right, so then this becomes we have multiplication, so we're going to add these terms, split and add the logs. So log base 2 of 3, getting a little tilty, I think that's the problem, plus log base 2 of x to the negative first. Now we take the negative first power here. It's an exponent. Drop it down front. This is now going to be the log base 2 of 3. Negative 1 or plus a negative 1 makes it a minus 1 times log base 2 of x. So log base 2 of 3 over x equals log base 2 of 3 minus log base 2 of x. So this is fundamental rule number 3. Which is that if you have log base b of x over y, this is going to be equal to log base b of x minus log base b of y. Save yourself a couple of steps. You can just use these shortcuts. All right, and one more. Sure, why not? Okay, so the last one is, what happens if we have something like log base 2 of x equals log base 3 of y? So in this particular case, there's no real way to solve this, keep in mind. But there is a way to translate this so that it's a much nicer type of thing. We don't want this to be log base 2 and log base 3 at the same time. This is really nasty. Don't let yourself do this. All right, try not to if you can help it. But what we can do instead is say, oh, well, that says that this log stuff over here is going to be of the form like 2 to a power, and this log stuff over here is going to be of the form 3 to a power. I think that's going to be really ugly if we try to do that. So instead what we can do is just focus on one. So let's focus on this one. Log base 2 of x equals a. We'll go back to this again. And now what we do is we say, okay, this is going to be 2 to the a equals x. Now what I'm going to do is I'm going to take the log base 3 of both sides instead of the log base 2. When I do this, it changes everything just a bit. So now here we have A comes down because we just did that exponentiation thing over here. So the A comes down front. Now it's A times log base 3 of 2 equals log base 3 of x. All right, well, we had A up here, so move the log over. Log base 3 of 2 is being divided from both sides. Oops. So now A, which was the log base 2 of x, is equal to log base 3 of x divided by the log base 3 of 2. So this is what's known as the change of base formula. So we're allowed to take any log that we want at this stage right here. You want to take the log base 3, you want to take the log base 10, you want to take log base e, which we'll get to in a minute, you want to take log base pi. You're welcome to do any of that. You could take any log that you want here. So the fundamental rule that drops out from this is that if we have log base b of x, this is going to be equal to log base c of x divided by log base c of b, the former base. So fundamental rule number 4. You can change any bases you want. Basically, all you need to do is turn it back into an exponential and then take a different log. But here it's a shortcut. So I kind of do it both ways in my head, mostly because in my pre-calculus back in high school, I actually proved the change of base formula, and then the teacher was like, great job, and then 2 weeks later it was a question on the exam, prove the change of base formula, because I did that. The class hated me. But I mean, it was an easy A for me because I came up with that proof. But the rest of the class, actually, it wasn't too bad because I went up to the front of the class, I explained it to everybody, and so it wasn't awful. They were just, slightly annoyed that Okay, in this case, then, we would also backfill and say that up here, log base 2 of x would become log base 3 of x divided by log base 3 of 2 equal to log base 3 of y. Then there could be different ways to try to solve this. If we actually wanted to solve for y, it's not pretty at this point. There's not really a point in solving it. It was just, let's get everything to the same base. So, yeah, that's about all we can do. Okay, let's see. There's probably other stuff here. Oh, E, right? So E becomes a super important number. Yeah, to anybody who noticed, I did get rid of the lo-fi, sorry. Every time I put it onto YouTube, they flagged me for copyright, so I was like, alright, let's just not deal with that anymore. Of course, the only punishment that they would give me is to give my revenue to the give my non-existent revenue to the people who wrote the music. So, I mean, it's going to a worthy place. It's just, I don't know, someday. That fanciful day when I have however many followers. All right, so anyway, in order to find out like what this whole E thing was all about. This is what's known as Euler's constant. So Leonhard Euler was a Swiss mathematician in the 1700s who came up with a whole bunch of really awesome proofs of, God, I mean, there's so much he did. It would probably be easier to figure out what he didn't do. At some point, he decided to kind of standardize all notation across a whole bunch of mathematics. And, I mean, he also invented a whole bunch of stuff too. But in his books, there were certain constants. Actually, pi was also named, or the Greek letter P was used to come up with the whole 3.14159 thing. He decided, or it wasn't even a decision, it was that when he got to this point in the book, he was on P. And so P got named for this value. And then everybody just started copying him and just saying like, okay, so P is now going to be 3.1415926, whatever. And you know, the ratio between the circumference and the diameter of a circle. And it started catching on, and people started trading all of this stuff. 3.1415926 was always then going to be the exact same value, and they always labeled it with the Greek letter P. Okay. And it just got used, and it's just one of those things. Later on, when Euler's constant was found, discovered, put into books and all that, I don't know if this was also in the same thing where this was the fifth constant, so it was E now, or if people just kind of used it and started using E because it was honoring Euler for his discovery. But obviously need to do more research. But what he was doing at the time was he worked for, I think it was Johann Bernoulli, one of the Bernoulli brothers at any rate, either Johann or Jakob. And as a graduate student, figured out that there was a particular value that he was looking for the compound interest formula. So for compound interest, you know what, let's back up then, and let's do this as simple interest first. Oops. So background. In order to find simple interest, the amount you're charged on your bill, so the amount is going to be equal to the amount you have in principal, so the initial amount that you had, or also this could be a sub 0 if you feel like doing that. So the principal multiplied by your rate, the interest rate, times time. Now the interest rate itself, if you just want the interest amount, this is going to be equal to P times your rate. But in order to get A, you also then need to add in the original amount you had. So that was P. Yeah, because you want, it's just going to be PR and T. This is not where PERT comes from. That comes later. So if the amount that you were getting charged in interest was the principal times the rate times the amount of time it's been, where these have to have common units and all that. Then what you'd want at the end of the year is that the amount would be equal to the principal that you started with plus That's in the wrong place. Boo. Okay. Principal that you started with, I should have done that first, plus the interest earned that year, which was going to be the principal plus PRT. You can factor out a P, and that becomes P times 1 plus RT. So this is your simple interest formula. Compound interest says, okay, not only are you going to be charged interest just on the initial amount by the rate and by the amount of time you had, you're going to be charged interest on the interest next time. So every time we calculate the interest on a certain compounding period, it's going to keep updating how much you owe, or potentially, in the case of bank accounts, how much you have in your bank account. So let's say A1 is going to be A0 times simple interest over 1 year. So this is going to be 1 plus R. We're not even going to do T right now because we're going to assume that this is at 1 year intervals. So A sub 2 is then going to be A sub 1 times 1 plus R. Well, A sub 1 was A sub 0 times 1 plus R times 1 plus R from this year. Okay, so that now is A sub 0 times 1 plus R squared. So then A3 is going to be equal to A sub 2 times 1 plus R, which then is equal to A sub 0. If we plug A sub 2, we plug in A sub 0 times 1 plus R squared. So this is now A sub 0 times 1 plus R squared times 1 plus R, or A sub 0 times 1 plus R cubed. So eventually this becomes kind of obvious that A sub t is going to be equal to A sub 0 times 1 plus R to the t. So this is like a super basic compound interest formula. But here's the thing. If you want to make it interesting, what we're going to do is split the compounding periods. So instead of doing compounding periods as just once a year, we could do this as now a function of t equals A sub 0 times 1 plus. If you do this throughout the year, you're going to split the interest rate, which is an annual rate, into n parts. You are then going to gain n compounding periods times the number of years that you're going to run this. This is where that formula comes from, this compound interest formula. You've probably seen this. The R over N is what's called the periodic interest rate. And NT is, not a Windows platform, going to be the total number of compounding periods. So there's a bunch of stuff you can do with this. If you invest $3,000 into an account that gets you 3% interest. I'm going to be very loose about that. No, that's not actually APY. It is APR for interest percentage rate, average, annual percentage rate. So it's at compounded quarterly. How much is this, bond or whatever it is, going to be worth after 5 years? So we could look at this individually and say that after the first quarter of the first year, what's going to happen is you're going to take a quarter of 3%, or 3/4 of a percent, of 3,000. Three-quarters of a percent is 0.0075. So if we multiply 3,000 by 0.0075, we are going to gain $22.50 off of the first quarter in interest. And then if we do the same thing, we take $3,022.50 and we multiply by 0.0075 again. This is going to get us now, for the second compounding period, $22.66.875. Now, if you're doing this realistically, the house always wins, and so you're going to round down for anything that's given to you, and you're going to round up for anything that's charged to you, realistically. If if you have an actual teacher rather than a business, this is probably going to be like, oh, well, just round normally, and only round at the end. Don't do the Office Space thing where you round at every quarter and shunt that into a bank account somewhere. So those fractions of a cent, right? So after the first 2 quarters now, we have a net gain of $22.50 plus $22.67 if we round that up. So that's $45.17, which now you multiply that $3,045.17 by our 0.0075, and this time we get $22.84 off of the next, or onto the next onto the next interest payment. There we go. So 45.17 plus 22.84 is 68.01. So then now we have $3,068.01 that was accumulated over, is that 1 year? Just double check real fast. 3,000 times 0.03. No, one more. So 3,068.01 multiplied by 0.0075 is $23.01. And that being added to 68.01 is going to be $91.02. There we go. So we have a net gain of $1.02 on compound interest, compounding quarterly, versus if it either compounded yearly or if we just did simple interest for 1 full year, because they are equivalent for short, or for within 1 period. All right, so the first compounding period, simple and compound interest are equivalent. So again, this makes it much more interesting. You plug these individual pieces into the formula. So A of 5, the time that we want here, is going to be equal to 3,000 times 1 plus 0.03 divided by n is 4 raised to the 4 times 5 is t is 3,000 times 1 plus, this is again 0.0075 raised to the 20th power. 1.0075 raised to the 20th, and then multiply by 3,000. So when we do this, we end up with a total 5-year amount of $3,483.55. So $483.55, it's not too bad, I guess. 3% return, given inflation, who knows, that might actually be the losing bet. But it's not too bad for sitting in a bank and being loaned out to other people. All right, so Euler decided to look at this and say, well, what happens if we start increasing the n value here, like substantially? So he said, all right, let's just do a simple case. This is going to be $1 at 100% interest rate, compounded annually. Nope, sorry, we're changing the compounding period. $1 at 100% interest rate for 1 year. So he said, okay, A of 1 is going to be equal to, we said $1, so $1 times 1 plus 100% interest is 1.00 divided by n raised to the n times t is 1. And really, this isn't a function on t anymore. This becomes a function of n. What is the amount we get back at the end of the year if we just say that we're having all of these conditions? So a of n is equal to 1 plus 1 over n to the n. And as n increases, as the number of compounding periods starts increasing and getting larger, the number in here, 1 over n, becomes a smaller and smaller number, but also we're multiplying it by itself over and over and over again. So it became an interesting question. If we increase the number of compounding periods infinitely, is this going to diverge to a specific value? Or sorry, to infinity? Is this going to converge to a specific value? Is this going to be potentially, well, it can't be 0, but is it going to be equivalent to 1? Or is it going to converge to a different value? As it turned out, it was converging to a different value. So if we look at this, all right, a of 1 is just going to be 1 plus 1 over 1 is 2. This is going to be 2 raised to the first power, so we just get 2. A of 2 is going to be 1 plus 1 over 2, or 1.5, raised to the second power, which is 2.25. A of 4 is going to be 1.25 raised to the fourth power, which is going to be 2.44140625. And that's off already. But anyway, that's all you really need to see. 2.44. All right, it's increasing. So what about A of 100? Right, so now we get 100 compounding periods in a year. This is now going to be 1.01, 1 and 100th, raised to the 100th power. Which is 2.704813.829, and some more stuff beyond that. Again, in terms of money, this is really all you're going to care about, is that we get $2.70 back at the end of 1 year if we do 100 compounding periods, compared to just getting our $2 back, or getting our $1 at 100% interest is $2 if you just did one compounding period, or simple interest. What about A at 365, so 1 per day? Okay, so 365 going for X, and then we get 2.71456748,202. All right, now it's going beyond money. At this point, Euler was like, oh, let's figure this out. It appears to be approaching a number. There were other techniques he used. It wasn't going to be, basic arithmetic. This would take forever. Trying to raise, even 1.01, trying to raise that to 100th power, that'd take a long time. So there are ways to shorten it, but it's not what he did. He figured stuff out. So A at let's go 1 million. So with 1 million compounding periods in a year, we end up getting 2.71828046932, which again, this is starting to approach a specific value. You can tell, right? The distance between 100 and 300 is a factor of 3, or increasing by 200, and we didn't get very far with our digits. We're still like about 1/100th away. We increased from 365 to 1 million. That's like a factor of, what, 30,000? Give or take, a little bit under that. And we've only increased by a matter of thousandths. So this is a tiny increase compared to the other. Okay, so as we start looking at larger and larger values, what Euler did was he found the limit as all right, he found the limit as n goes to infinity of 1 plus 1 over n to the n. And he found out that this exactly equaled that e value that we saw before, which can be approximated as 2.7182818459045, and this keeps going on forever. There was a time when people didn't know if this was like a, is it a rational number? Is it an irrational number? Is it a what's known as transcendental number? Does this go well beyond being able to find it as a solution to polynomial equation? Is this going to be, something like pi? And it turns out that it is. So this is a transcendental number. It is unable to be found as a solution to any polynomial. You can approximate the solution by polynomials, but the value itself doesn't ever. So he started using this as what's known as the natural base. Now the reason it's called the natural base has to do with calculus. Specifically that this was on a number file video actually the other day, but it was like a week ago. Anyway, yeah, one of their regulars came on and highlighted the fact that taking the derivative of e to the t ends up getting you e to the t. So you're looking at what is the slope of this particular exponential function. It's the same as the function itself. So it just keeps calling itself over and over again. So this is the natural base because of that. So people have used this for all sorts of stuff, not just interest, compound interest, but also population growth. So if you want to look at the growth of a population of a certain group of people, or certain, ducks out in the wilderness, certain plants that are not being predated, then you're able to use exponential functions. So unbounded exponential growth. Invasive species would be one. So an unbounded population growth, oftentimes they use E just because it's nice and easy, especially if, again, you want to find, if you want to find derivatives of any kind at some point, you want to do calculus with it. It's just easier to use the natural base. It is awkward sometimes due to the fact that the exponent might have different kinds of terms in it, and it might have like a natural log in there buried somewhere. But it works okay. So like one example might be something like if you wanted to find out well, let's see, you want to do chemistry, so so the amount of a particular reagent in a substance will decrease exponentially, so it will be, let's just go with halved every 2 seconds. Let's say that they're started out with 50 grams at t equals 0. And you want to find when it reaches, let's go with 0.3 grams. So, I mean, the structure of this particular problem doesn't matter. I could have done population growth. I could have done half-life in terms of radioactive decay. I could have literally done anything. It's all going to be the same structure. So here we're saying that the amount at any given time t is going to be equal to the initial amount a sub 0 times, in this case, because it's halved, I would just use that as your base. Like, don't use e unless you have to. So a sub 0 times a half raised to, this gets interesting, t over delta t is the easiest way that I can explain this. So t is going to be your time, delta t is going to be the amount of time it takes for this base to be multiplied again. So the base is going to be multiplied again every 2 seconds. So this, as long as t is in seconds, delta t is just 2. We started with 50 grams, multiplied by 1/2, raised to the t over 2. Okay, and then here again we want to find when is this going to happen, when are we going to reach 0.3 grams, so we can plug that in over on the left hand side for unknown, or for the known value that we have for the amount, and then the unknown value is going to be our t. So 50 times 1/2 raised to the t over 2. Now at this point you can use whatever log you want to find this. It doesn't matter. It's not like I'm going to care. I would suggest getting the exponential term by itself. So divide everything by 50. This is going to be 3 over 500 if you want to balance that fraction, is equal to 1/2 raised to the t over 2. And again, if you want to use base 2 or base 1/2, you can do that. It's up to you. I honestly, I like using my just real quick script here, so I do natural log. Just, that's it. I always use natural log. So the natural logarithm is going to be the log with base e of something, whatever that's going to be. So we use our base of 2.718281828459145, etc. And here then we use the logarithm rules that we had from earlier. So this is the natural log of 3/500ths. You can split stuff up if you want, but honestly, I'm going to keep it together as one term as much as I can. It just makes it easier. Is equal to, this is t over 2 comes down because it's the exponent, times the natural log of 1/2. We can then divide both sides by the natural log of 1/2. So the natural log of 3/500ths divided by natural log of 1/2. And we can multiply both sides by 2 in order to get rid of that 2. And that's equal to t. Okay, so now we get 2 times the natural log, parentheses, 3 over 500 divided by the natural log of, parentheses, 0.5, 1/2, whatever you're doing. And so this gets us a t value of a very small number, comparatively. 14.7616 seconds. If you're doing significant figures, good luck to you. Most of the time that I'm doing stuff with timing, realistically, I'm just saying, okay, this is probably close to 14.76 seconds, and I will deal with that. If I want it to higher precision, sure, why not? But realistically, I don't know, 15 seconds sounds good. Or slightly less than 15 seconds. Yeah, 50 grams. I didn't put in the decimal point, I guess. So. Yeah, mathematicians don't generally use sig figs unless we absolutely have to. You know, when we're looking at precision, we're mostly looking at, like, I mean, yes, eventually we'll look at how accurate is this number, but generally speaking, we're going to look at what units do we want at the end first, and maybe we'll figure out the, like, you know, maybe we'll figure out the error bars on it later. All right, there's all sorts of other cool stuff we could do. Again, half-life is literally the same thing. If you did, like, I don't know, (936 grams) decays into 489 grams after 10 days. You want to know when will it be less than let's go with 10 grams. So this is some radioactive element. You have no idea what it is. Compound even. No idea what this is, but 936 grams decays into 489 grams after 10 days. When is it going to be less than 10 grams? In this particular case, I don't generally do this with my students, just because it's not necessary. But this is actually more of a question you'd actually have in a lab. So, you know, you're doing experiments, and this is what you see. These are the measurements you get. So, so we know that, for instance, A of t is going to be a sub 0. We can now do this as e to the kt, just because this is going to be some unknown, you know, we're not going to find half-life in this, so we're not going to use a particular base. So we could just use e. And again, it makes it much easier to use natural logs, so why not? And now we have two pieces of data. So first of all, a sub, or a at 0 is going to be, right, a sub 0 e to the k times 0. So this is just 1. So a sub 0 is the at times 0, where we had 936 grams of the substance. And a at 10 days is going to be equal to 936. And over here we had 489 as the total amount. 936 times e to the k times 10. So we know what t is here. That's our 10 from before. We don't know what k is, which is our decay rate. Usually you call it a growth rate, but in this particular case it's a decay rate. All right, we're going to divide by 936 onto the other side, which, you know, technically you shouldn't have a triple equation like this, but that's fine. As long as you're doing it to all of the pieces, we're good. So this is e to the 10k is going to be equal to 489 divided by 936. That's really far away. Let's move that over there. Okay. And then here again, easiest log to take is going to be the natural log. Not just for ease of swiping the pen this time, but actually because the base is e. So this makes it nice and easy. The 10k comes down front, and then we're multiplying by the natural log of e, which is just 1. I guess technically that's a fundamental rule as well. The log base b of b is always just going to be 1. And this is equal to the natural log of 489 divided by 936. All right, divide by 10. So k is equal to 1/10 natural log of 489 over 936. Whoops. So if you want to do this, one of the ways that you could do it is just store this number somewhere in your calculator and just pull it up as needed. Another rather psychotic way to do it is you could actually plug in this value and then say, oh look, there's a natural log and it's on a base of e, so these are going to end up being inverse operations of each other and cancel out, with one slight modification. The 1/10 here has to be knocked up inside the argument of the natural log, which then is going to make it 489 over 936 to the 1/10 power, or take the 10th root of 489 over 936, and that's your new base. So it depends on what you like. I don't like doing that, just generally. So then our a at t, we want to know when is it going to reach 10 grams. This is 936 times parentheses, no, we're not doing that, right, e to the k, again, just plug that whole mess in times t. And again, we don't know what it is. Divide over your 936. So this is 10 over 936 equals e to the kt. We know what k is. It's a constant. That's okay. And again, take the natural log of both sides. Natural log of e to the kt is going to just be kt. Equals natural log of 10 over 936. And then divide by k. That ugly mess down there. So natural log of 10 over 936 divided by, and again, you could actually write it out if you wanted to, 1/10 natural log of 489, 89 over 936. There's no nice way to simplify that either, so nope, nope, nope. So this is going to be, one more time, natural log of 10 over 936 divided by parentheses 0.1 natural log parentheses 489 over 936. Nice. So t is going to be approximately 69.91 days. And again, you figure out your own accuracy later. I, as a mathematician, will always demand that the exact answer is somewhere on the paper. And then if you want to round that to a reasonable amount, right, this is somewhere right around 70 days. It's probably fine. All right, so I think I'm going to get going. This has been fun. And yeah, so just letting everybody know, I'm going to be broadcasting on Friday again for Outer Wilds. It's going to be the after hours again, doing a, what was it? Yep. Oh, Achievement Hunter. So I'm going to be going for the Achievement Hunter stream and try to get as many as I can in the entire night. Hopefully 100% it, but we'll see how it goes. And then I'm taking the week after that probably off due to just some stuff that's going on outside. So yeah, it'll be all good. So I will see Lana on Discord. But I will see hopefully everybody else on Friday, and not next Wednesday, but the Wednesday after that. That is the, what is that, 3rd, 10th, 17th. So I'll see everybody on the 17th of February. Hopefully all is well and don't need to worry too much. All right. See you all later. Have fun. And this is Obi-Wan Pez signing off for N Simplex Pachinko. Oh, right.